Welcome! In this video, you will see the mass balance for an activated Sludge process. In the activated Sludge process shown below, is treated a wastewater flow rate of 12,000 liters per minute. The bacterial concentration in the aeration tank is 3 grams per liter. Meanwhile, the bacterial concentration in the settling tank is 10 grams per liter. And the treated water leaves the process without these microorganisms. In this process, the activated Sludge flow rate is continuously returned to the aeration tank. Assuming a steady-state continuous process, compute the flow rate of water that leaves the aeration tank and the flow rate of activated Sludge returned to the aeration tank. Step 1. Draw the flowchart of the process. This is the flowchart of this process. F1 represents the wastewater to be treated in the aeration tank. This stream represents the airflow required to perform the process. The water stream withdrawn from the aeration tank is transported in the stream F2, which has a bacterial concentration of 3 grams per liter. This stream is introduced in the settling tank. The treated water, F3, is withdrawn from the upper part of the settling tank. F4 represents the stream of activated Sludge return to the aeration tank. The bacterial concentration of this stream is 10 grams per liter. Notice the bacterial concentration in the aeration tank is 3 grams per liter. Step 2. Classification of the process. As it was described before, this is a continuous process because there are simultaneous inputs and outputs of mass in the process. Besides, this is a steady-state process due to the fact that the flow rates and concentrations in the respective streams and process units remain unchangeable during the process. As we can see, F1, the wastewater to be treated in the aeration tank, has the same value that F3, the treated water. This is established because this is a steady-state process. Step 3. Analysis of the mass balance equation. The mass balance equation is here. Input of mass, output of mass, production of mass, consumption of mass, and accumulation of mass. This is represented by a simplified equation. As we said before, this is a steady-state process. Therefore, there is no accumulation. Both consumption and production terms are removed from the mass balance equation because the bacterial concentration in the reactor remains constant. It means that the same amount of all microorganisms is continuously replaced with young microorganisms at constant rate. So, the microorganisms' concentration remains unchangeable in the process. According with this paragraph, consumption and production are removed from the equation. Thus, the material balance equation is given by this expression: inputs of mass equal outputs of mass. Step 4. Overall mass balance in the reactor. To perform this overall mass balance, we use the equation of 10 before. In this case, we can see two streams entering into the aeration tank F1 and F4. Both streams are introduced into the aeration tank. Therefore, F1 plus F4 represent the total entrance of mass to the aeration tank. F2 is the single stream withdrawn from the aeration tank. This flow is placed here. So, when we substitute the known data, we obtain this expression. As can be seen, this balance does not provide a solution to the problem because F2 and F4 remain as unknowns of the problem yet. Step 5. Component mass balance in the settling tank. As we can see, the microorganisms only are present in streams F2 and F4. Thus, the input of mass flow of microorganisms is given by this product, F2 multiplied by its concentration. Similarly, the output of mass flow of microorganisms through stream F4 is determined by this product, F4 by the corresponding concentration. Of course, this is the microorganism's concentration. Hence, the mass balance for microorganisms is given by this expression. Input of microorganisms equal output of microorganisms from the settling tank. Again, F2 and F4 are the unknowns of the problem. Step 6. Solution of simultaneous equations. We have next equations, equation 1 and equation 2. Equation 1 represents the overall mass balance, while equation 2 represents the component mass balance. So, the substitution of equation 1 into equation 2 provides this expression. After some simple manipulation, we determine F4, the activated Sludge stream. The value is 5,142.86 liters per minute. The substitution of the previous value into equation 1 gives F2. Therefore, the water flow withdrawn from the aeration tank is 17,142.86. Step 7. Include the results in the flowchart of the process. Here we are, F2. The water stream withdrawn from the aeration tank. And also F4, the activated Sludge flow rate returned to the aeration tank. Thank you for watching.